In this episode, it gives me great pleasure to introduce Professor Arunan, Professor and Chair of the Department of Inorganic and Physical Chemistry at the Indian Institute of Science in Bangalore. Professor Arunan did his Masters in Chemistry from the Indian Institute of Technology, Madras, his MTech from the Indian Institute of Technology, Delhi, and his PhD in Physical Chemistry from Kansas State University in Manhattan, Kansas, on the applications of infrared chemiluminescence in chemical reaction dynamics, and his postdoc on microwave spectroscopy from the University of Illinois at Urbana-Champaign. Professor Arunan is an experimental physical chemist focusing on the spectroscopy and dynamics of molecules and clusters. His research interests also include chemical kinetics and reaction dynamics, shock-wave interactions with molecules and materials, hydrogen bonding, intermolecular bonding and interactions, and also astrochemistry and astrophysics. The main experimental tools he uses to understand intermolecular interactions are supersonic expansion to cool molecules to low temperatures, enabling the formation of weakly bound complexes, which are then probed by microwave spectroscopy. Let me add that Professor Arunan was recently elected Fellow of the Indian National Science Academy, among other honors, in recognition of his outstanding work on hydrogen bonding and weak interactions. In this first episode, Professor Arunan will be speaking to us on defining the hydrogen bond. With my first question. So, you have been working both experimentally and computationally on chemical bonding and chemical structure and microwave spectroscopy. So let me ask you, what is conventionally meant by a chemical bond? Because the description, the definitions have not really stayed constant over the years and over the centuries. And how do you view the concept of a chemical bond?
See, now I have to give you two answers to this because convention is one thing, my views are different.
Absolutely. That's why I phrased it in two different questions.
Yeah. Let me tell you the convention, which is somewhat unfortunate. Most people think of a covalent bond when a chemical bond is mentioned, which is sharing of electrons between two atoms. And this is really unfortunate because this is what has led to a lot of needless debate and controversies. So maybe I can just...
So you mean it explicitly excludes the ionic bonding and other non-shared bonding?
Let me just keep this. So this is the introduction I had, intermolecular. And this has really bothered me often. I think this is somewhat relevant. You are seeing the harmonic oscillator and Morse curve, isn't it? Are you able to see them?
Yes, yes.
Yeah. See, typically when we talk about a bond, we think about the distance, and let me also see if we are able to see the pointers.
Yes, I can.
See, if that's good. Two atoms are at this distance, people say it's bonded, and if the distance is far away, then we think of them as not bonded, which is typical. But this is not enough. For example, if I say the distance between the two atoms is Rg, equilibrium distance, but the two atoms have energy somewhere here, which is much higher. Should we call it bonded or not? It's a question. Of course, the rigorous answer would be that it's probably bonded for half a vibration. For example, if it has this much energy above the dissociation energy, if there are only two atoms, classically, quantum mechanically, it doesn't matter. If the energy the two atoms have is higher than the dissociation energy, as we are talking about only a diatomic molecule, there is only translational, rotational, and vibrational energy. Let's say the total energy is.
In the limit, you can say that it is almost a free particle moving on a rugged potential surface.
That's correct. So the more, in my view, technically correct answer is that it's bonded for half a vibration. Basically, they may be moving towards each other or away from each other. They're moving towards each other, they will go hit this potential well, bounce back, and separate as two separate atoms.
And when you say half a vibration, the vibration period will be infinite.
No,
if it is dissociated, if it goes all the way to infinity, then
no. When I say half a vibration, the vibrational frequency is here. It's basically the time taken for it to hit and come back. It is here the time taken for it to leave this. It will be very short.
So time taken to hit the potential wall,
that's the
and
period.
Come back to the equilibrium position.
That's correct.
No, not going the other way, because the other way it will go to infinity.
No, but then it's not bonded. It will be bonded only when they are within this well.
Right. Okay.
So basically the time taken for it to leave the potential.
Okay.
So it would be most probably sub-femtosecond in this high energy. The typical vibrations are like 10-20 femtosecond, depending on many things, but it will be like that time scale. So we cannot say it is bonded. So not only the distance, but also energy is important. Dynamics. That's one point. The other point is, if we talk about polyatomic molecules, people will always ask me what is diatomic molecule. Only physical chemists are interested. What about polyatomic molecule? This is the water structure we normally draw. But we don't put this bond between two hydrogen atoms. How do we know that? Of course, that's what we are taught. And so typically covalent bonds have been shown by this line. Of course, we put a double bond means 2 lines, triple bond 3 lines. So most chemists think of covalent bond when they say chemical bond. But that's really unfortunate because, I know if you've seen this Coulson's valence book was very popular. He says a bond between two atoms has become real, tangible. I can almost see it. Then I wake with a little shock, for a chemical bond is not a real thing, does not exist. No one has ever seen one. Now, up to this point, I could sympathize with Coulson because in 50s, all this was true. But he also said no one can ever. This is a figment of our imagination. This is some statement no scientist should ever make because nobody really knows what will be possible tomorrow. So
never say never.
Never say never, absolutely. You can say, I am not able to see it. That's perfectly fine. Nobody can ever is a statement no scientist should ever make. But anyway, he was quite convinced. So that's why I said chemical bond has confused experts and novice. And now they are saying it's chemical bond. Everybody thinks of covalent bond. This may have been due to Pauling's book. In fact, I wrote in a news item kind of thing, chemical bonds are made of electrons, and we can see them now. Now this is an AFM image of the pentacene. We almost see the same way organic chemists draw. Basically, there are electrons between the two atoms. So that's our typical covalent bond when two atoms share electron. But then in high school itself, we learn all this. Covalent bond is a region of likely high electron density between nuclei, which arises at least partly from sharing of electron and gives rise to an attractive force and characteristic interlink distance. And this is from Mayupak. It also says, look at agnostic coordination, hydrogen bond, multicenter bond, and they don't mention ionic bond here. And hydrogen bond, which is they write it's a form of association between highly electronegative atom and another little electronegative, and they do mention this NOF here. It's intermolecular, intramolecular, and without a few exceptions, most of them are like 5 to 6 kilocalorie per mole. And this is what IUPAC had in 1994.
Yeah,
We
actually,
had, yeah.
the former was a question that was even asked during my candidacy meeting. When I was talking about electron density and bonding and all
Yeah,
that.
yeah.
And so one of my professors, who was an expert on X-ray diffraction, he brought up in inorganic material. So he brought up a case of metal-metal bonding, where there is no buildup of electron density in the
Sure.
internuclear region, but
Yeah.
still there's a bonding.
Yeah, in fact, I will address this with specific examples.
Mhm.
If you look at the ionic bond, this is 1999. To be honest, I looked in 97, wasn't there. Ionic bond is written as the bond between atoms with sharply different electronegativities. Let me go back. Covalent bond is a region, hydrogen bond is a form of association. Ionic bond is the bond between two atoms of sharply different electronegativities. In strict terms, ionic bond refers to electrostatic attraction experienced between the electric charges of cation and anion, in contrast to the pure equivalent bond. In practice, it's preferable to consider the amount of ionic character of a bond rather than referring to purely ionic or purely covalent bond. This is true. No bond is 100% covalent or 100% ionic. But I don't know why chemists conventionally didn't think of ionic bond when we say chemical bond. Because
So
tell me.
Yeah, no, I was saying, so in this scheme, so the covalent bond and ionic bond are seen as two. But where does the hydrogen bond fall in this classification?
I can tell you. It falls
There's been a lot of controversy over the years whether ionic bonding is covalent, whether it's ionic.
I will that. In fact, to be honest, hydrogen bond falls everywhere. There are some hydrogen bonds which are really strong symmetric, they would call it. They are almost covalent. And some weak hydrogen bonds are, it's difficult to see any covalency. In fact, in 1999, two experimental results were published. One is NMR, another is Compton scattering. In NMR, they saw the spin coupling between two nitrogen atoms bound through hydrogen in H ... And with the spin coupling measured 7 hertz, they were able to guess the percentage covalency. They estimated it to be 5 to 10% covalency. What was interesting, Pauling in his book is electrostatic interaction, no covalence at all. But Pauling, being the genius he was, he also looked at the, in fact, I will talk about this more. He looked at the distance between OH in water and then H ... O in the next water molecule, this HO distance. He said this is longer. He used some exponential bond order model and he said maybe 5% covalent. And that's exactly what experiment showed. Compton scattering also showed the evidence for bond between the next O. They could see OH, HO, OO, all of them in Compton scattering. In fact, when this was published in 1999, I had joined IPC department in 97. Professor Balram was the editor of Current Science. Of course, he's also interested in this. And he gave me the paper with NMR evidence for covalency and said, Arunan, you are interested in hydrogen bond. Can you read this paper and write a news in Current Science? Research news. So I agreed. I wrote hydrogen bonding efficiency forward in Current Science. But let me take you further. Why didn't chemists think of ionic bond also as a chemical bond? This is an unfortunate mentioned. Says no accumulation of electron density between the atom. So what? If you look at potassium chloride in the gas phase, it's K plus Cl minus. And I have microwave evidence for this. If you are familiar with the quadrupole coupling, chlorine has a spin 3 halves. And this has a quadrupole moment. Couples with the overall angle, leading to splitting. The quadrupole coupling constants could be measured from the microwave spectroscopy. In HCl, this coupling constant is like 100 plus megahertz. In KCl, it's very nearly zero, 0.05 megahertz, 5 orders of magnitude smaller than HCl. This would be the case only if Cl minus is there with a spherical charge cloud. Now, HCl is a covalent bond. The electron density around chlorine is not at all spherical. In KCl, it is spherical. And the dipole moment of KCl is very close to 1 times the distance between the two atoms. So this is a very clear evidence that potassium chloride is ionic in gas phase, not just solids. But if you read this definition, it says mostly in solids. Because KCl in the gas phase, nobody worries other than gas phase physical chemists doing microspectroscopy.
Right.
Others don't think about KCl as a, but you can produce KCl gas and collect astrophysicists. Yeah. In fact, as you may know, astrophysicists have a very simple periodic table: hydrogen, helium, and metals.
Metals, yeah.
That's what astrophysics is. So depending on the field, it will change. But this is very unfortunate. I don't know why we almost gave away the ionic bond. KCl, there is certainly a bond between K and Cl, but there is no accumulation of electron density. But there is some electron density, which is small. You know what's really interesting? What Coulson said about chemical bond is verbatim the same as what Van der Waals said about molecules 100 years before. Van der Waals said 1860s.
Yeah, I think Leonard and Stark, they had a running feud with Boltzmann, which probably also contributed to Boltzmann's suicide, and about the reality of molecules.
Molecules, because now we can laugh about it, or we know molecules exist. But when we walk, we are walking through nitrogen and oxygen. We can't see them. So it is not easy. And of course, Van der Waals was only looking at ideal gas law, and he realized both assumptions are wrong. One is that it's a point mass because they must occupy some space. Another is that there is no attraction between them. In fact, he introduced these constants A and B. Now, I used to ask students, Van der Waals, if we didn't know, came from a carpenter family. His father was a carpenter, and not only in India, all over the world, societies, governments suddenly think we should educate all the children. So Van der Waals was sent to a school later in his life. And then he submits his PhD thesis when he was 36 years. Now, you know, if you are 36 when you submit the thesis, you cannot imagine a career in science. Most people won't take you. But Van der Waals was 36 when he submitted this thesis, having this equation. Now, every student studying high school would have learned about Van der Waals. So I suspect he chose these two constants as A and B because of this modest background. If he was like Aristotle or from a family, he would have called it alpha and beta. which should have sounded cool, for a constant in science. But van der Waals, but because of this, all intermolecular interactions were called van der Waals attraction, van der Waals forces, van der Waals interaction, and B was called van der Waals radius. When two atoms touch each other without bonding or interacting. So this set influenced physicists and chemists. So all intermolecular forces were called van der Waals forces, and the two atoms touching each other without bonding, that is called van der Waals radius. But then,
of course, when we say touching each other, that implies a radius, right?
yeah, certainly. Otherwise, you can't define a radius. That's why, Sukumar, I realized the major difference between physicists and chemists. Physicists like to unify things. Chemists like to classify things. Everything was van der Waals forces until
chemists and
the first half
biologists
of,
also.
of
Biologists
course, yeah.
also like to classify.
Classify, because that's how, for chemists, we start with the periodic table. In fact, at times I feel like Mendeleev should be household name like Darwin and Einstein. What he has done is no less than what Darwin and Einstein did.
Sure.
But somehow chemists always fall between. And when Pauling looked at the structure of water, ice, and H2S, before Pauling, Latimer and Rodebush had looked at water and concluded that the hydrogen held between two octet constitutes a bond. I will show this in more. They speculated a hydrogen bond between molecules of water. And Pauling had this crystal structure. As you would know, crystal structures don't give hydrogen atom. Hydrogen doesn't diffract much at all. So they know only the heavy atoms. So Pauling knew each oxygen was surrounded by 4 oxygen. But when you looked at the H2S, each sulfur was surrounded by 12 sulfur. So I put a pack of oranges here. This is central one, 6 around, 3 on top, 3 at the bottom, which is not shown here. So each sulfur was surrounded by 12 sulfur. Each oxygen was surrounded by 4 oxygen. This was somewhat confusing because H2O and H2S are both C2E molecule. And if you look at one molecule, they have the same structure, similar structure. The angle and distance are different.
Yeah.
But in bulk, they were as different as apples and oranges. So Pauling called this a hydrogen bond.
Ice and oranges.
Yeah, what you can say. In fact, apparently Germans use pears rather than apples. So they say pears and oranges. But whatever it is, they are
so
different.
Here it seems that there's a sharp distinction between the hydrogen bond and the van der Waals interaction. Is it always possible to make such a distinction?
No, let me stop you 1 second. Hydrogen bond was clear. That because each water is surrounded by 4 water, and they thought the 2 hydrogen bonded to the 2 oxygen, and of course chemists know lone pairs. 2 lone pairs interacting with 2 hydrogen. This was van der Waals equation was there. So they said this is van der Waals interaction. So I found out once chemists understood something, they gave a name, particularly in this field. When they didn't understand, van der Waals interaction.
Okay.
Because I can show you a number of evidence to prove what I am saying. When something was understood, a name was given, particularly intermolecular interactions. When they didn't understand, if you ask someone what is hydrogen bond and what is van der Waals interaction, there was no answer. Of course, you see, we have put a dashed line. This is covalent bond. This is some dashed line, dotted line. And chemists were particular about this line between two atoms indicating a bond. They thought there's a bond, so they put dashed line here. And many scientists, including the paper I sent you yesterday, were uncomfortable calling this a bond. So in German literature, as of today, they call it a hydrogen bridge.
Okay.
They don't call it a bond because bond was reserved for covalent bond. Now, in H2S, if you look at it, okay, there is no hydrogen bonding, but how are they sticking together? It's a solid now. And if you look at water, it seems like I have one water molecule. The next water molecule, if it approaches oxygen, hydrogen should come close. If it approaches hydrogen, oxygen should come close. Otherwise, they won't bond, stick. In H2S, this didn't seem to matter. Any orientation of H2S, they just stick together. So this is, in fact, very convincing. Pauling wrote H2S as hydrogen bond. Water has hydrogen bond, H2S has no hydrogen bond. And this was very influential. Pauling is certainly one of the most influential chemists in 20th century. So people would say H2S has van der Waals interactions. And if we then ask what is a hydrogen bond, so it will be Latimer and Rodebush wrote this. Latimer and Rodebush were in Berkeley, where Lewis was a towering figure. Lewis had come up with this octet model in the 1910s. And they were thinking about water. There is no crystal structure, no NMR, nothing. They just look at the bulk properties. And they say water shows tendency to both add and give up hydrogen, which are nearly balanced. Basically, they say H3O plus is known, OH minus is known. But if you look at ammonia, ammonium ion is well known. NH2 minus is not as well known as OH minus. And if you look at chlorine, Cl minus is well known. ClH2 plus is not as well known. Of course, as a physical chemist, astrophysicist, we may be able to make ClH2 plus.
Sure.
But for a common chemist, particularly in 1920, so they said water shows tendency to both add and give up hydrogen, which are nearly balanced, but other atoms don't seem to have it. Then they said a free pair of electrons on one water molecule might be able to exert sufficient force on a hydrogen held by a pair of electrons on another water molecule. Such an explanation above saying that hydrogen nucleus held between two octets constitutes a weak bond. They didn't want to violate Lewis' theory. So they were very careful. You cannot say Lewis is wrong.
It's 1920 after all.
Yeah. So they knew it's beyond what Lewis has told. But they found a way to write things that hydrogen held between two octets constitutes a weak bond. In fact, there were others who suspected hydrogen bond, suggested it, but Latimer and Rodebush was the first to say constitutes a weak bond. So Pauling's book on nature of chemical bonding mentions this as the first paper to mention a hydrogen bond. Now you see the.
So this is pre-quantum mechanics.
Absolutely. Pre-quantum mechanics. Now, what is this hydrogen bond was a major problem. So Pauling wrote it must be electrostatic interaction because there is probably a O minus H plus, not +1 -1, but delta, some partial positive charge. And he said it may be interacting with the partial negative charge. From that time, many books say dipole-dipole interaction. But I think this is not I will skip some of these details. Pimentel and
mostly
material
with the highly electronegative atoms were the ones that were considered to form
because
at
they
that
were
time,
easy to find. They were easy to find.
hydrogen bonds. Yeah.
See, Pauling said it has to be electrostatic as it cannot be chemical. He had covalent in mind. If you know Israel Chvili, he has written a very popular book on surface and intermolecular forces. And he says no more than a particularly strong type of directional dipole-dipole interaction. No bond. And I'm sure you know the infrared redshift and the intensity enhancement. In fact, if there is a hydrogen bond, for example, if OH has a hydrogen bond, the OH stretching frequency after hydrogen bonding reduces from the free OH. The intensity also increases. And this cannot be explained by simple electrostatics, I mean dipole-dipole interaction. But when I talk to physicists, for example, Sriram Ramaswamy in our physics department, he says no physicist would ever think two dipoles interact without induction. But chemists think electrostatic and induction are two different forces. He says no two dipole will interact without inducing each other. It's just impossible. But
the only
all our
forces,
energy,
the only force through which molecular materials interact is the electromagnetic force, right?
Electromagnetic force.
Yeah.
See, that's why it depends on your background and everything.
Yeah.
So electrostatic, inductive, dispersive, charge transfer covalency, exchange repulsion all play varying roles. In fact, Sanjay Vatagonkar and TFR had several papers saying dispersion dominated hydrogen bonds. So there is really no single physical force that can be attributed to hydrogen bonding. In fact, the statement I included in the IUPAC would. But it was very common
can be
at that
attributed exclusively to hydrogen bonding.
Absolutely, yeah. And if we look at FHF minus, that the binding energy is like 160 kilojoules per mole, almost 40 kilocalorie per mole. They call it strong symmetric hydrogen bonding. Now, if you look at neon HF complex, that has a geometry which is linear, FH neon. That's very weak hydrogen bond. It might have dipole-induced dipole, not just dispersive forces. What also I found is that in this confusion, a lot of people started equating London and van der Waals. London was the first to come up with the dispersion relation. Even to rare gas atoms, eventually condense if you cool it down to low enough temperature. There is no charge, no dipole moment, no electrostatics, but why are they still binding together? He realized that only the average equilibrium distribution of electrons around argon or neon is spherical. But at any given instant, there could be fluctuation and there could be an instantaneous dipole. And the instantaneous dipole could induce a dipole in the neighboring atom and they get correlated, leading to a stabilization. So basically, the London dispersion force depends on the polarizability of the two atoms, and the more strongly polarizable, the stronger the interaction. But van der Waals, when he realized the molecules attract each other, he had no clue about electrostatics or dipole moment charges. So in my view, van der Waals interaction should be one time for all intermolecular interactions. And later on in the first half of 20th century, for D by derived an expression for dipole induced dipole interaction. London for instantaneous dipole-induced dipole. All these van der Waals. And of course, we know it's not just dipole. So you have to worry about multipoles, quadrupole, octupole. You can write an expansion. So all electrostatic, inductive, and dispersive forces. But then there is also a possibility of a covalent bond between molecules, not just within molecules. So all of them contribute to hydrogen bonding.
So actually, I think
yeah.
Feynman he disputed the conventional thing, the fluctuating dipole-dipole view, and he said it was attraction of the nucleus for its own displaced electron density, which is causing the van der Waals interaction. Of course, the whole thing depends on what is self and what is non-self, right?
That's correct.
Your own electron density or the other person's, other molecule's electron density.
See, displaced electron density, why does it display?
Polarization.
The displacement due to the polarizability. So London basically wrote that. In fact, if you remember the expression of London, it is polarizability. In fact, I have all of them. But I used to I don't have it in this present. If you look at D by Kisam and London, but I have written a few articles in Resonance discussing this in more detail. Kisam, D by and London. So van der Waals could be called Kisam, D by and London together, including multipoles. In fact, let me just give you one very good example. In fact, this may be a good slide to discuss. You know, if you look at attractive and repulsive interactions between humans, you may be able to understand them better. Now, if you look at these are two men almost shaking their hand, touching each other, and smile on their face. You might think they are bonded or they are friends. And here again, there are two men. Look at the contact, it's very intense, but we can't call them bonded. This is like an anti-bonding, but if you look at this, which is typical in maybe UP or even Bombay suburban, there is plenty of contact. There is no bonding or anti-bonding. This is what crystallographers call as breaking or non-bonding. The van der Waals radii is from this. They are in touch with each other, but they are not bonding. But then for humans, if you look at this, there is really no contact. Still from the face, you can conclude that they are friends. And if you look at this again, there is no contact at all. But you look at the face, you know they are not friends. Because this is something I really like. You know, there's plenty of contact. It's almost like one atom saying, I want to bond with you, another atom saying, don't come near. You know, in general, humans have faces and you can see if they like you or don't like you. And of course, we can also hide our emotions, like maybe like this. We can smile in public.
Yeah.
But atoms
and of
have
course,
no faces.
all these interactions are time dependent.
Absolutely.
There can be attraction one day and repulsion the other day.
Yeah, for humans. But thankfully for atoms, there's no life. There is no emotion, no feeling. So two
It
atoms
depends on how many electrons you add.
Yeah. So the two atoms behave the same way under most of the conditions. Like they don't change colors like humans do. That's what enables us to study them. You know, the atoms also rarely have like, if one atom is attracted to another atom, we only when both are attracted, we can see them.
Of course, we are talking about ground states. When you talk about
ground state, excited states, you can see everything. So mostly the materials, atoms, molecules, they behave the same way, whether you study them or I study them. All over the world. That's what has allowed us to study chemistry and physics, because they are not moody and they don't change the behavior depending on the day, time.
I think that's as good a time as I need to stop for today, and we will continue next time with Professor Arunan. Thank you, Professor Arunan.